Okay, for this problem is the pi P has a mass of 800 kilograms and is being driven into loose sand using the uh, 300 kilogram hammer, which is dropped a distance of 0.5 meter from the top of the pie. Determine the distance of the pie driven into the sand after one blow. If the sand offer a friction resistance against the pie of 18 kilonewton. Okay, the coefficient of restitution between the hammer and the pie is equal to 0.1, and we will not consider the impulse due to the weight and the weight of pie and hammer, and the impulse due to the sand during the impact. Okay, we actually the weight of pie and hammer is heavy enough, but if we compare with the impulse from the impact, is maybe it can be neglect for that case. Okay, so for this problem, we may state of our problem first. For the first step, okay, as if we consider the hammer falling down, which is the free falling problem, this is the conservation of conservative system. That is that we have just only the hammer. Okay, that's this. If we consider a free body diagram, we have just only the weight of the hammer falling down here, and and because it just has just only the weight, so the weight is the conservative force. So then this is the conservative system, and then we can apply conservation of energy principle just in order to find the final velocity of the hammer before impact. Okay, before it hit to the pie. Okay, this is just the first step. We use the conservation of energy from point 1 to point 2. We get the velocity of hammer at step 2. Okay, and after that, if we consider the impact between hammer and pie, okay, we will apply the conservation of momentum and coefficients of restitution to determine the velocity of pie and velocity of hammer after impact. Okay, and then after we know the velocity of pie, okay, we will consider just only the pie. That we apply the principle of work and energy. We will not use conservation of energy because it has a friction force. Friction force is non-conservative force. We cannot use conservation of energy principle. We have to back to the principle of work and energy instead. That is we will have the work done of the friction now. And after we apply this principle, we can determine the distance of the pie that has been driven. Okay, we may starting with the first step. Okay, that's when the hammer is free falling from the air, and we have the weight here. Okay, and for this case, we apply the conservation of energy just only for hammer. That is because it is the hammer. It just has just a little weight, and it is a conservative system. So then we can apply here. We set datum at the final position at the floor, and so for this case, it's the hammer is drop off without the initial velocity. So then it means that the kinetic energy at the first position is become 0, and according to we set the datum at the floor, so then the potential energy is above the datum. Potential energy is due to gravity is the weight times h, and it is positive. It is above datum. Okay, and it will be negative. It is below the datum. Okay, so now for the first position, it is above the datum, so then it is positive. And at the final position, that is the step 2, the state at the state 2. The pi will have the velocity. Okay, that is we use the notation of V2 for the hammer. Sorry, for the hammer, it's not the pi. Sorry, a half mv square is the kinetic energy for the hammer at the final position. And because it's at the datum, so then the potential energy at this position is become 0. So according to this, we substitute the each value that we already know from the problem. We substitute the weight of hammer, that is 800 kilogram. G is become 9.81, and H now is equal to 0.5 meter. And this is the weight of the part of hammer also. Sorry, the weight of the hammer is 300. Sorry, okay, my eye is it's maybe bad now. Okay. So it's 800 kilogram for hammer. Okay, the weight of the hammer is the mass of the hammer is 300 kilogram. Okay, and after that, after we solve this equation, we obtain the velocity of the hammer at the final position is 3.13 meter per second. Okay. So after that, we move to the impact of them. Okay, for the impact, we know that now we know the velocity of the hammer. Okay, and that is when it's hit to the part, we have V2 already, and V2 of the hammer, and this is the V velocity of the part. Okay, VP1. That is actually we may change the notation a little bit. That is before impact. That is we change it to be VH1 now. That's actually we determined it already. For it's equal to V2. Okay, so VP1 because the pi is maybe at the stationary. It's the velocity of pi and before impact, this is equal to 0. So then we apply the conservation of momentum. Okay, you see that from this equation. Okay, actually, we H1 we already know from the previous step. We already know VP1 we already know, but VS2 and VP2 this is the unknown. So for this case, we have just only one equation, but we have two unknown. We have to use the additional equation that is coefficients of restitution. Okay, now that is defined by this. Actually, what is the coefficients of restitution? If you consult with the textbook, you may find out the coefficients of restitution is the ratio of the relative velocity, okay, of the particle separation just after impact. Okay, we just from this equation, it's maybe same like this, but actually it's come from the definition of the ratio of the restitution impulse. Okay, that is the impulse. That is after the impact is occurred and it's the particle will leave. Okay, the impulse, that's the at the state that the particle will leave each other to the deformation impulse. Okay, that is equal to the impulse after the impact. So the impulse at the state of impact. Okay, that is when we consider two particle, two part of we have two particle, right? Hammer and pi. When we consider two particle for the value of E, and we write the equation, we can obtain this equation that is become the ratio of relative velocity of the particle separation just after impact. Okay, something like this. So according to this equation, we can define that for the impact. That is, if E is equal to 1, it means that we call it like the elastic impact. That is the no energy loss. Okay, for this case, actually, it is the ideal case. It is the ideal case. Actually, it's the has to not happen because it has no system that has no energy loss. Okay, but it's maybe very close to 1 for some case. And for another type, that is maybe E equal to 0. For this case, we call the plastic impact. Okay, that is the loss. The kinetic energy is the maximum loss for this case. That is the particles is go together. That is two particles after impact, two particles go together. Okay, that is for the additional detail for the coefficients of retribution. So after this, we substitute the value that we already know. For the mass of the hammer, we know that it is equal to 300 kilogram. And we know the velocity of the hammer from the first state. That's we already have the velocity of the hammer before impact. Before it hit the point is equal to this. Okay. And for the mass of the pi, that is equal to 800 kilogram. Okay, and velocity at the initial state is for the pi is equal to 0 now. Okay. And after that, we is equal to the momentum after, okay, after impact. That is equal to 300 vh2 and 800 vp2. These are unknown now. Okay, and we have to unknown, and we have to use the additional equation, that is coefficient of restitution. That's the problem is give us that the coefficient of restitution now is equal to 0.1. Okay, so we substitute in this equation, we can have the additional equation. Now we have equation 1 and 2, and we solve these two equations. We obtain the velocity of pi and velocity of hammer. Okay, you see that it is positive, right? Okay, we have to set up the positive sign function now. That is actually we may set up goes down at the positive 1. Okay, so for this case, we found out this is positive, so then it should be goes down. Both hammer and pi goes down, but you see that the velocity of pi is higher than the hammer. So then it means that the pi is moved separate with the hammer. Okay, so then both are falling down, but it's not go together. Okay, so from this, okay, we consider to the pi, especially for the pi here. Okay, we will apply the principle of work and energy because uh, we know that it is not conservative system. It has a friction. Friction is a non-conservative force. Okay, non-conservative force is what? Okay, non-conservative force is the force that the work done of this force is depend on part. Okay, this is just the non-conservative force is defined like this. If the work done from this force is depend on part, it is the we call it like the non-conservative force. And in opposite way, the conservative force is what? Conservative force is the force that the work done of this force is not depend on part. Okay, it's not depend on part. It depend on only its position. Okay, it's depend on position only. The work done is depend on position only. Okay, it means work done. Okay, for this case, if the force that its work done is depend on only its position, so we call it is a conservative force, like the gravity force. Example of this is just like the gravity. Or elastic spring force. Okay, this is just the types of this example. That is actually for most engineering problem. Okay, we working with just only the gravity force and elastic force. So then in many application, we can apply the principle of conservation of energy for solving the problem. But if the problem that we consider is the has the friction force or any type of force that depend on part, that is work done is depend on part, we cannot apply the principle of conservation of energy. We have to back to principle of work and energy instead. Okay, so for this case, we would like to find the final position here, that is become the state 3. Okay, and we know the velocity of the pi after impact that we already determined is equal to this. Okay, so then it's equal to the kinetic energy at the second state plus the work done from second state to third one. Okay, and the work done from the second to the third is composed of, if we consider the free body diagram of the pi has the weight, that is mass of pi times g, and we also have the friction force. Friction force actually form the soil. Okay, so the weight, the work done from weight, because it goes down is the downward and the positive rate. Okay, it goes down, and the weight it goes down also. So the weight work do works in the same directions of the displacement. So the work done of this force is positive. Okay, and for the friction force, the force is opposite to the motion of the pi. So then the work done of this force is the resistance force. So then it's become negative. Okay, according to this. So we would like to find D here. Okay, and at the final position, we know that the pi is stopped. So then it's become 0. Okay, so then according to this equation, we can solve for D. Okay, that is become 0.03479 meter, and then we multiply with 100 to convert it to be centimeter. We have this value. Okay, that is complete this problem.